Hello everyone. Today we will start looking into a new method of investigation. By new I mean that we have not seen this, right? That is gravity methods. If you recollect, we had seen initially electrical methods under which we had seen electrical resistivity, cell potential and induced polarization method. Then we had a look into some special methods under electrical. Next is the gravity methods of investigation. Right. In gravity methods is based on Earth's gravity, where Earth's gravity is defined as the force of attraction of bodies on the surface of the Earth towards the center. Right. So, we are able to stand, or I am able to sit here because of the gravitational pull which I experience. Right. The gravity increase toward the center of the Earth and decrease when we move away from the center of the Earth. It is obvious because gravity is defined as the force of attraction of the bodies on the surface of the Earth towards the center of the Earth, which means when you are closer to the center of the Earth, we are going to feel higher gravitational pull. When you are much away from the center of the Earth, for example, if you fly at an altitude of 10 kilometers, the gravity which we experience will get reduced. Right? So, gravity which we feel depend on the distance at which we are from the center of the Earth. Further, Earth's gravitational field is not constant. We are going to see the reasons little later. As of now, let us remember gravitational field is not constant. Earth's gravity is a vertical force, right? Vertical force and with a vectorial character, because wherever the object is attracted towards the center of the Earth. So, it is a vertical field vector. Gravity entirely depend on the density of the mass. Right. For we were saying attraction of bodies. Right. The attraction of body depend on the density or density of the mass, and gravity in turn depend on the density of the mass which is on the surface of the Earth. For example, this is the ground surface, this is the center of the Earth. We are talking about a body here. The gravitational pull that this particular body experience is depend on its density. Right. So, we are looking into the fundamentals as usual. We are looking into some fundamentals initially, then we will move on to the actual method of exploration or understanding the subsurface using the gravitational field. Gravity method is based on Newton's law. Newton's law, especially the first law, states force of attraction between two masses separated by a distance r is given by this equation, where F is the force of attraction, which is equivalent to the constant which is known as gravitational constant multiplied by mass m1 mass m2 divided by square of the distance of separation. Right. So, force of attraction between the two masses m1 and m2 separated by a distance r is given by F is equivalent to G multiplied by m1 multiplied by m2 divided by r square, where G is the gravitational constant which is given here. Right. So, this is the Newton's first law. Suppose if you consider Earth as a sphere and it is not rotating and it is of homogeneous nature everywhere, right, and radius is r, right. So, then if the equation can be written as F is equal to G multiplied by capital letter M, small letter m divided by R square. Right. Here earth is capital letter M and small m is the small mass on the surface of the earth as I have drawn. So, let us say this is the surface of the earth, there is a small mass m, mass of the earth is given by small letter m, and we have assumed earth is homogeneous and it is not rotating and it is spherical. If it is so, as per the Newton's law, F is equivalent to G multiplied by capital M multiplied by small m divided by R square, where R is the radius of the earth. Right. As per the Newton's second law of motion, F is equivalent to mg, where the small letter g is given by this, right. Small letter g is nothing but g divided by r square, at the top we have m, gm divided by r square is given by letters g. So, when you solve for g, it is nothing but g is equivalent to gm divided by r square. However, we very well know this assumption is not correct, isn't it? Because we know earth is elliptical and it is rotating and it has got irregular surface and internal mass distribution is also not homogeneous as we assumed, right. So, all this causes gravity vary over the surface of the earth. So, it cannot be estimated simply using this Newton's law. So, what is important now is acceleration of a body, right, when it falls due to the gravity, right. So, acceleration due to gravity, which is the small letter g, right, which is nothing but acceleration of a body freely falling under the influence of gravity, is defined as acceleration due to gravity, right. Acceleration due to gravity, small letter g, is equivalent to 980 Gal, which is nothing but centimeter per second square. So, when we are discussing about the acceleration due to gravity, the unit Gal is named after the scientist, which is Galileo, who has given a definition of our understanding of acceleration due to gravity, right. The unit of acceleration due to gravity g, right, which is meter per second square, which is the SI unit. SI unit for g is meter per second square, and which is also stated as 1 Gal. 1 Gal is equivalent to 1 centimeter per second square, right. And the unit of g, as I told you, is usually length divided by time square. If the unit is in centimeter per second square, it is equivalent to 1 Gal, and Gal is also can be converted in terms of seconds. So, if it can be 0.01 meter per second square, all this is referred as Gal, named after Galileo, right. However, Gal is a bigger number in gravity exploration or gravity investigation. Hence, we do not use Gal, but we use milli-Gal, which is 1,000th of a Gal. So, 1,000th part of a Gal is known as milli-Gal. So, milli-Gal, which is shortly referred as m-Gal, is the unit which is often used in gravity investigation or gravity survey. However, some people and some books refer the what is known as, instead of milli-Gal, they use a unit known as GU, which is gravity unit. Gravity unit is 1 gravity unit is equivalent to 0.1 milligall. Okay. So, this is the unit which is often used, right. Many of us use unit known as milligall. Some people use the unit of gravity unit, right. So, 1 gravity unit is equivalent to 0.1 milligall. Right. Normal value of G at the surface of the earth is equivalent to this, right. It can be referred either in any way, right, 9.8 meter per second or 980 centimeter per second square. So, when you refer it as centimeter per second square, it is equivalent to Gall, as we had seen here. So, 980 centimeter per second square is equivalent to 980 Gall. Thousandth of that is 980,000, which is milligall, which is equivalent to 9,800 gravity unit. Usually in gravity investigation we use either milligall or gravity unit. So, this is with regard to the G, which is referred as acceleration due to gravity, and the units we have seen usually we use milligall or GU, which is the gravity unit. Why the acceleration due to gravity vary, right? We had seen already Earth's gravity vary. Why the acceleration due to gravity vary? One of the big reason for that is the large scale variation in the gravity, right. Why? Because we already know any mass on the surface of the earth is attracted toward the center of the earth, right. In the denominator we had a letter r, which is the radius. We know very well radius of the earth is actually different depending upon the latitude. Hence, there is the expected variation in the earth's gravity due to the change in the radius of the earth. This leads to large scale variation of gravity, which is associated to the latitude of the earth, right. So, acceleration due to gravity varies due to latitude due to two reasons or two effects. One is the shape of the earth, right. As you can see here, the radius of the earth is 21 kilometers more at the equator than that of a pole, right. So, between the center to the pole, either north or south pole, the radius of the earth is 21 kilometer less than the radius measured along the equator, right. So, radius play a role, because if I go and stand here, right, I am 21 kilometers closer to the center of the earth. If I stand at the equator on the surface of the earth, I am 21 kilometers away from the center of the earth compared to that of poles, right. So, due to this reason, Earth's gravity is greater at the pole than the equator, because the mass, when you keep it at the pole, is closer to the center of the earth. When the same mass is kept here, it is further away from the center of the earth. Due to this reason, the same mass, let us say x, when you keep it on the pole, right, it will experience nearly 5186 milligall more gravitational pull or acceleration due to gravity. So, this is one reason. So, the acceleration due to gravity vary over the surface of the earth, that is dependent on latitude. One reason for that is the change in the radius, or in other words change in the shape of the earth, right. Then the second reason for the variation is centrifugal acceleration. Centrifugal acceleration reduces the acceleration due to gravity. Why? Because earth is rotating. Since earth is rotating, right, as the earth is rotating, the mass on the surface of the earth faces or feels the centrifugal force, right. The centrifugal force will be actually highest at the equator, right. It is something like when you are on a merry-go-round, right. Imagine this is a merry-go-round. The merry-go-round may be something like this. You may have inner one which usually have a bench wherein you can sit, right. You can sit, whereas the outer rope may have something like a horse, right, on which also you can sit, right. So, where will we feel the maximum centrifugal acceleration? Here compared to this place, right. So, and further when you are just standing on the axis of rotation, this is how it is rotating, this merry-go-round. When you go and stand here, you do not feel any kind of centrifugal acceleration, isn't it? Similarly, right, on the surface of the earth, when you are at the equator, we are going to feel very highest rotational velocity compared to if you move towards north, and if you reach the pole, you do not feel centrifugal acceleration. Similarly, when you move toward the south pole, the centrifugal acceleration decrease. So, Earth's rotation also has an effect on the gravitational pull. Because of the centrifugal force, right, the object here tries to fly away from the surface of the earth. This reduces the gravity, right. So, all these black arrows indicate the gravitational pull. The gravitational pull is affected by the centrifugal acceleration. Since this body wants to fly away from the surface of the earth due to the rotation of the earth. As the earth rotates, this body wants to fly away, due to which it experiences comparatively lesser gravity if the same body is kept somewhere here. Okay. When the same body is kept on the pole, it experiences maximum gravitational pull because it does not undergo any centrifugal force, right. So, this is the second reason for the change in the gravity or acceleration due to gravity. If I go back, so why the acceleration due to gravity vary? One reason is large scale variation in the value of acceleration due to gravity, that is due to latitude. There are two sub reasons, there are two effects. One is the change in the shape, that is the radius. Radius here is 21 kilometers, less than the radius between the center to the equator. So, this causes change in the gravitational pull or acceleration due to gravity. Second reason is earth is not only a kind of a spinoid, but also it rotates. So, earth's rotation also causes the gravity vary. So, that means gravitational pull at the equator is less compared to that of poles due to the centrifugal acceleration, right. And on the previous slide we saw gravitational pull here is less because of the higher radius here. Here we say gravitational pull is little bit reduced because of the centrifugal acceleration. These are the two reasons for large scale variation on the surface of the earth, which is controlled by the earth's latitude. Then apart from this large scale variation, the gravity value also is likely to vary over the surface of the earth due to some small scale objects present beneath the surface. In fact, in exploration, this is what is of great interest to us, this is what we want to study, right. That means small level variations, right, in the density of rocks also lead to change in the gravity which we experience at the surface of the earth, right. Imagine that you are standing here, right. That means you are over a denser body present below the surface of the earth. So, this is the surface of the earth, below there is a dense body over which you are standing, which means you are going to experience comparatively higher gravitational pull. Acceleration due to gravity over here is comparatively higher because beneath us we have a big dense body, right. So, when you measure the acceleration due to gravity on the surface of the earth from here, the gravity value increase, as you see here it is increasing. It is maximum here because just below that you have the high dense body. As you move, as you make measurements here, gravity value decrease, right. If you look at this sketch, here there is a major discontinuity, fault in the earth, right, along which the body of the earth has moved upwards or this side has moved downwards, or anything could have happened. This could have partly moved up, this could have partly moved downwards, or this would have stayed at the same location, whereas this alone would have moved downwards. So, let us not worry about that. Let us see today the dense body is present much closer to the surface of the earth here. This is the depth to the dense body, whereas on this side the dense body which was supposed to be here has gone very much below, right, due to which when you make the measurement of gravity on the surface of the earth, gravity value is less. From here it is increasing because on this side dense body is closer to the ground surface, isn't it. So, this is how the variation in the subsurface also causes some minor variation in the gravity which we measure on the surface. Imagine this is the ground surface, right. Imagine there is a everywhere below we have gold. Here everywhere beneath the surface we have coal. Right. Gold has got very high specific gravity, nearly 18.5 to 19 gram per centimeter cube. Coal's density is very less, maybe depending upon the type of the coal, the density may vary from 2 to 3.5. So, when you make the measurement of gravity on the surface of the earth, right, value of gravity will be much higher, here it will go down, isn't it. So, this is the impact due to change in the density of material present below the surface of the earth. Imagine you are flying, this is the sea, this is land, and sea thickness of water let us assume as 5 kilometers. So, when you make measurements from here to here, the gravity value will be comparatively higher in the land part, and in the sea part it will come down, because here this 5 kilometer is solid matter, even let us assume it is of coal or sand, clay, whatever we assume, the density here will be comparatively higher than that of the sea water. The density of sea water is only about 1.025. Any soil, earth will be at least of density certainly great density will be greater than 1, it will be around 2. So, due to which density which we measure here, or sorry, the acceleration due to gravity which we measure here will be more than what we measure over the sea. So, this is what we are interested in. So, this actually helps us to delineate the different rock bodies present below the surface of the earth by making the measurement of Earth's gravity or acceleration due to gravity.